Hi, welcome back to the channel. This is chapter 7, worked example. Bearing pressures on a strip foundation, worked example. Give a concise account of the manner in which soil is assumed to fail under shallow foundations. Hence show that in figure 7.1, which I'll show in a minute, the summation of the components of the passive forces Py gamma, PPC and PPQ dash give rise to a limited bearing load Q per unit length of footing, where Q equals 2 P dash cos delta minus phi plus 2 PPC cos delta minus phi plus 2 PQ dash cos delta minus phi plus BC tan delta. Hence justify the form of the equation for the bearing pressure on a strip foundation of infinite length. Q equals gamma B over 2 N gamma plus C dash NC plus Q dash NQ, where C is the cohesion and Q dash the surcharge. ULUC, don't know what that is. That the source of the question? So here's figure 7.1. We got width of foundation. This is surcharge ground level. Then the mass of the concrete, then the bricks. The width of the foundation is B, then there's like a triangular section underneath. Is that supposed to be the bearing pressure? That's a really accurate diagram, isn't it? And then the slip plane goes all the way around, figure 7.1. So there's that's figure 7.1. Solution. A shallow footing is one where a breadth B equals equal to or greater than Z, the depth to the base of the footing is Z. If the footing is infinitely long, the problem may be regarded as two-dimensional. The assumed form of failure at ultimate limit state as is shown on figure 7.2, and no rotation occurs. Right, so it kind of squishes and then it fails in two planes. So you've got a slip plane. So basically, I think the whole point of this is that the soil doesn't really fail doesn't fail directly underneath, like, I don't know, like in compression or in a block underneath the foundation. It's in a massive chunk. These two massive sort of arced slip planes. It's not like you would imagine. I never imagined that the soil would fail like this. I just thought it would go, like fail in a chunk right underneath it, sort of like maybe, oh, this is cohesive. So this is a cohesive, isn't it? So it wouldn't fail like a sand. So a wedge of soil XYZ, so XYZ is that triangular wedge. A wedge of soil XYZ is assumed to move downwards with the footing, producing lateral thrust to the left and right, which, when the soil fails, overcome the passive resistance of the soil along either side of the footing. The form of failure is a slip along the plane ZHF and ZIG. ZHF on the left side on this picture and ZIG on the right side. In order to analyse this form of failure, it is assumed that wedges XHF and YIG are in a state of passive plastic equilibrium. Wedges XZH and ZYI are zones of radial shear. Oh, radial shear. Whoops. Y, Z, I. So H, X, F. Oh, the two triangles on the furthest outside are in a state of passive plastic equilibrium. Could do with colouring them here. Wedges X, Z, H, and Y, Z, I are zones of radial shear. The soil above the level of the base of the footing does not contribute to the shear and resistance of the soil but acts as a surcharge load. Consider the free body diagram showing the forces acted on the wedge of, turn over. So it's got Q dash and then the ground level is called D, E, F, G, H, I, and then Z, X, Y, Z, delta, and that 45 minus 5 over 2, which is, still quite complicated, isn't it? Sorry, turning page. So this is an enlarged version of that, the wedge under B. Doesn't even, it should say X, Y, Z. That little diagram is X, Y, Z. Q, and then it's got delta, and then C, and then P, PP, PP, delta, delta. Oh, sorry, phi and phi. Soil under the base of the footing. Here, Q, the load per unit length of footing. C, cohesion along face of wedge equals C, B, 2 cos delta. PP, the total passive resistance force acting at phi to the normal. For the limiting condition when the footing is just in equilibrium and on the point of failing by sinking into the ground, the sum of all the vertical forces, I can't remember what that symbol is, epsilon V, or sum of V equals 0. Therefore Q downwards equals 2C sine delta, with the vertical component of that little C value, plus 2PP cos delta minus phi. The total passive force PP is made up of 3 components. PP gamma representing the resistance of the wedge ZXHF. PPC represent the cohesive resistance of the soil. PPQ dash representing the resistance provided by the surcharge. PP gamma. PP gamma. The resistance of the wedge. Maybe I should just go back one. XH. What was it again? F. XHF. XZHF. Right. Right, the whole wedge. That's XZHF. The whole wedge on the left. Thus, substituting for C and PP, the limiting bearing load length of footing Q equals B. Then, substituting for C, cohesion, and PP, the limiting bearing load unit length of footing Q equals B equals C, Q equals B, that's the width, isn't that the width, times C tan delta plus 2PP gamma plus 2PPC plus 2PPQ dash cos delta minus phi. God, it's quite complicated. You need more diagrams, but it will just take a whole page, wouldn't it? For a perfectly smooth base, delta equals 45 plus phi over 2, but in the more likely case of a rough base which prevents the soil at the top of the wedge spreading, delta equals phi, then Q equals 2 PP delta plus PPC plus PPQ dash plus BC over 2 tan phi. If the following dimensionless symbols are introduced, ny n gamma equals 4pp gamma divided by gamma b squared, then nc 2ppc divided by bc plus tan delta nq equals 2pq divided over q dash b. The equation becomes q equals, oh my god, it's quite complicated, isn't it? Sorry, I just saw that equation, it's so long. Q equals 2 gamma b squared times n gamma over 4 plus bc divided by 2 nc minus bc over 2 times tan phi plus q dash b nq divided by 2 plus bc over 2 tan phi equals b gamma b over 2 n or gamma plus c nc plus q dash nq. And pressure per length, pressure allowable bearing, oh, the pressure applied allowable unit length Q, because Q over B, oh right, yeah. The pressure per unit length, isn't that the width? Oh, the pressure per unit length. Q equals gamma B divided by 2n gamma plus C NC plus Q dash NQ, where n gamma, NC and NQ were all known as bearing capacity factors. So that's it then. That was the first question. I'll obviously go through this again because that was quite difficult. It's quite frightening. That equation's terrifying because it's so long, so complicated. But I'll go through it and I'll write it up again, and then it'll be easier to understand. Thanks for watching. Hopefully you still enjoyed this video. Please like and then subscribe to the channel. Thanks.